All right, let's talk about a paper that truly taught computers how to see. It's called DeepLab, and it tackled one of the toughest challenges in computer vision, teaching a machine to understand an image, not just as a whole, but pixel by single pixel. That incredibly detailed job is called semantic image segmentation.
Now take a look at this picture. For you and me, it's a no-brainer. Two people on a motorcycle. But for a computer, that's just a giant grid of colored dots, millions of them. The real puzzle is, how do you teach a machine to see the rider, the passenger, the helmet, and the bike, all as separate, distinct things?
And that's really the heart of it. It's not enough to just draw a big box around everything. True understanding means that for every single pixel, the computer has to make a choice. Is this pixel part of a leather jacket, or is it part of the motorcycle's shiny chrome? That's the mind-boggling level of precision we're aiming for.
Now, to really get why DeepLab was such a bombshell, we got to rewind the clock a little. Before this paper came along, the best tools for the job were deep convolutional neural networks, or DCNNs, and they were awesome at saying, yep, that's a picture of a cat. But for segmentation, they really struggled, all because of a big built-in trade-off.
As the paper points out, these DCNNs had three huge hurdles. First, to get the gist of an image, they'd shrink it down over and over, and all the fine details would just get blurred into oblivion. Second, they were terrible with objects of different sizes. A huge truck up close versus a tiny one far away? Total confusion. And third, because of all that shrinking, they were just awful at figuring out where an object's precise edges were. They knew a cat was in there, but they had no idea where the cat's fur ended and the couch began.
So, this is where DeepLab comes in and just changes the game. The researchers didn't just point out these problems, they came up with three incredibly elegant solutions that, when you put them together, completely rewrote the rules.
The first big idea is called atrous convolution. It sounds super technical, but it's actually pretty clever. Atrous literally means with holes. Think about it like this. Instead of scanning a map by looking at every single tiny square, you poke it with your fingers spread far apart. You get a feel for a much wider area, way more context, with the same number of touches. This let the network see the bigger picture without having to shrink the image and lose all that crucial detail. The second innovation, ASPP, just builds on that first great idea. If one set of spread out fingers is good, why not use a few sets, each with a different spacing? Well, that's atrous spatial pyramid pooling. It probes the image at multiple scales all at the same time. One set of fingers is close together for fine details, another is spaced out for medium features, and another is spread way out for the whole scene. And boom! You've solved the problem of seeing objects at all different sizes.
And finally, the finishing touch. Even with those first two tricks, the network's output was still a bit, well, blobby. So the authors brought in a classic technique called a conditional random field, or CRF. The best way to think of the CRF is as a detail-obsessed artist. It takes the network's rough, blurry sketch, looks back at the original image's colors and textures, and just cleans everything up, snapping those fuzzy boundaries to the true crisp edges of the objects.
Now, I can talk about this all day, but the impact of this final CRF step is absolutely stunning. You really have to see it to believe it.
Okay, let's look at the airplane here. On the left, that's the raw output from the network. It's kind of blobby, the edges are all fuzzy. But look at the image on the right, after the CRF has worked its magic. The mask is just perfect. It's sharp, it's precise, it's perfectly tracing the wings and the tail. The improvement is just night and day.
Now let's try a harder one, the bicyclists. On the left, the raw prediction is a total jumble. The riders and bikes are all mushed together. But after the CRF, on the right, you can see this clean, beautiful separation between the person and the bicycle. It's so much better at picking out these distinct objects, even when they're all tangled up.
And one last example, look at the dog. The initial prediction is pretty vague, right? But after the refinement, the mask accurately captures all these fine details, like the exact shape of the ears and the curve of its back. It is literally the difference between a rough guess and a detailed, genuine understanding.
So these visuals are incredible. But to really make a dent in the scientific community, you gotta bring the receipts. You need to prove it with hard data. And DeepLab did exactly that, setting a whole new standard for performance.
At the time, the Olympics of this field was the Pascal VOC 2012 benchmark. The score is called MIOU. Basically, it's a measure of pixel accuracy, and higher is always better. The top methods before this were stuck around 65 or 66%. DeepLab just blew right past them.
And that's the number that matters, 79.7%.
This wasn't just a tiny step forward. This was a giant leap that completely reset what people thought was possible and established a new state-of-the-art. But the true test of a great paper isn't just the final score. It's the influence it has. And the ideas from DeepLab didn't just win a competition. They became the fundamental building blocks for pretty much the entire field of computer vision moving forward. As the authors themselves put it, the impact was immediate. All of a sudden, other top research groups started adopting atrous convolution and that CRF cleanup step. These ideas became part of the standard toolkit for anybody working on this kind of problem. And that influence stretches right into the tech that we all use every single day. That self-driving car that needs to tell the difference between the road, a pedestrian, and another car, that's built on these principles. The software that helps a radiologist find a tumor in a medical scan, that's segmentation. Even the virtual background on your video calls, the magic that separates you from your messy room, that is a direct legacy of the work pioneered in DeepLab.
So DeepLab really taught computers how to see the world with an incredible new clarity, one pixel at a time. It solved some really fundamental problems, and in doing so, it just unlocked a whole new generation of applications. It really leaves you wondering, now that the computers can understand what they see with this level of detail, what will they see next?
This is for entertainment purposes only.